Today we have Professor Onur Mutlu here, and first let's congratulate you on winning the Maurice sorry
Maurice Wilkes.
Maurice Wilkes Award, and thank you for accepting this interview. And I'm sure that it will provide a great opportunity to let the students in the world, especially in China, to know more about you and your research.
Yeah, thank you very much.
And let's start the question from the early years.
Okay.
So the first question is, you were born in Turkey and had a bachelor degree in Michigan. Most people, I think, in Turkey went to U.S. after the bachelor. Can you tell us when do you decide to move to U.S. and why did you move to U.S.?
Okay, that's a good question, actually. First of all, thank you very much for this interview. I appreciate that. I'm happy to win the award, and I'm really happy to do this interview for anyone who's interested, certainly the Chinese students. So I was born in Turkey, yes, and it's unusual for someone to go after high school to the U.S. In Turkey, I actually started a university called Bilkent University, which is one of the top universities. But if the way you get into a university in Turkey is you go through an entrance examination. Lots of students take that examination. And if you actually do well, at the time I took the examination, Turkish government offered the top students the opportunity to do their bachelor studies outside Turkey. There are a bunch of countries, I think US, Canada, Australia. I'm missing some things, but yeah, Switzerland was one of them, I believe. UK also, yes. There were 5 or 6 countries where you could choose. So I took that opportunity, basically. Essentially, it was a scholarship that the government provided, because if that didn't happen, I would have stayed in Turkey, because we couldn't afford really going to the having a bachelor's education in the U.S. otherwise. So that's the reason I went to the U.S., because I felt it was a good opportunity, and I applied to a bunch of schools in the U.S. Michigan was a good one, and I decided to go there. But I first started the university in Bilkent, so I spent some time over there, worked at the computer center, learned about computers over there actually initially, and then transferred to Michigan.
Okay.
Speaking of studying computer science, when we look at your CV, what's interesting is that you have both degrees in computer science and also psychology. So that's a very unique experience. How did you feel about psychology, and why did you choose computer engineering eventually?
That's a great question also. Let me go back to the university entrance examination that I mentioned. The way it worked at the time I took it, it was in 1996, was there were 2 steps. In the first step, it's an elimination step. It basically reduces the number of students from, at that time, 1.5 million to maybe 500,000 or so. And then the second step, what happens is you basically decide your path for the future. And the way you decide your path is you essentially say, okay, I'm going to be an engineer or scientist. Then you need to take a very hard test that consists of science, math, and Turkish topics. And also you need to say, okay, I want to go to this school and this department. So you basically create a ranked list of which school and which department you want to go to. You basically create that list and then take the exam, and then afterwards there's processing that goes on that figures out where you should be according to everybody who made the list and the score that you got in the exam. So I was interested in computer science. I was actually interested in many things. I was interested in international relations, but my father told me that don't go to international relations, and he was right actually, because his advice to me was, he said that if you're a great engineer, great scientist, you can always do international relations. And I feel I know what he means a little bit right now, maybe. This doesn't mean that international relations is bad, but he encouraged me to go to science. So my first choice over there was computer science. The second choice was molecular biology and genetics. And I went into my first choice. So I was always interested in computers. That's why I went to computers. But let's go to Michigan right now. So when I went to Michigan, or before I went to Michigan, I was always interested in psychology also. So I took a bunch of psychology classes in high school. And when I went to Michigan, I saw the opportunity that you could actually do 2 degrees, which is a very hard thing to do in Turkey, actually. But in Michigan, you had the opportunity. So the first class I took was actually Psych 111 at that time. It was a huge class taught by a wonderful teacher, James Lloyd Hilton. And I really enjoyed it. And I decided, okay, I could do a degree in psychology also. But I was also interested in computer engineering, so I decided to follow both. So it was not a choice between computer engineering and psychology. It was more that I was very interested in psychology, so I decided, okay, let me do a degree in that also. That was wonderful.
Yeah, wonderful.
Yeah.
Yes, and we know that you got your PhD at UT Austin with ILPAT. And did you start working with ILPAT at Michigan?
You found good questions, huh? So, no, actually, the answer is no, because when I stayed in Michigan for 3 years, and when I became ready for research, ILPAT had already moved to University of Texas. But I actually took my first Introduction to Computing Systems class from ILPAT in winter 1998, and he was another great teacher. And I really enjoyed the class, and he really cares about teaching and research. So when I was applying for graduate school after three years, he was actually visiting Michigan once in a while because he had students there also. I went to his office and talked to him, said, I'm interested in applying, would you write me a recommendation letter? And he looked at my CV, he looked at my score in his class. He always tells me that I was not the top student. I was the second. But at least there were more than 400 students. That was a good part. Then he said, yeah, of course I would write you a recommendation letter. And I also expressed my interest in working with him also at that time. And he said, I would take you immediately. I will also write the recommendation letter. You need to go through the process. But so there was a bond between us, I think. I really liked the style. He really liked me, and we clicked for sure, and that's why I decided to work with him at that time, but not at Michigan.
I see.
Nearly every student in our community knows about ILPAT, but the interactions are mostly during conferences. As one of the best students of Yale, can you describe the advising style of him, and did it also influence how you interacted with your own students?
I see. That's a good question also. Yeah, I guess you have a lot of good questions in stock for me. First of all, I'm not sure if I'm the best student of Yale, you know. let me. There are a lot of great students that Yale raised because of his advising style. I don't know if you know Wen Mei Hu. Wen Mei is one of Yale Pat students, and he's actually the first winner of the Maurice Wilkes Award.
Wow.
If you go back to 1998, when the award was first instituted, Wen Mei won the award. So I don't want to claim that I'm the best student of Yale because he had a lot of great students. That was one of the reasons I worked with Yale, actually, because of his advising style. And essentially, how do I summarize it? Essentially, Yale focuses a lot on fundamentals. Basically, you want to do fundamental research. You want to advance the fundamentals of computer architecture. That's where you want to work, for sure. And also, his advising style is relatively hands-off, in the sense that he gives you a lot of freedom to explore your own ideas. He gives you feedback at the right times, but he leaves you free much of the time. So he created the environment in his group such that the group focused on fundamentals. You have a lot of freedom. You can interact with really strong students together so that you can do great research. And I really enjoyed that style, for sure. So has it affected the way I interact with my students? Absolutely, yes. I think because I fundamentally like that style, so I adopted it also. Maybe I'm a little bit more hands-on than Yale, but I'm also younger at this point, earlier in my career. But certainly, I think it's really important to focus on fundamentals and also give a lot of freedom to the students. I don't know if does that answer all the questions you asked?
Yeah.
Okay.
Yeah, so now we're going to talk about one of your research, run-ahead execution. So how do you come up with that idea, and what inspired you with that?
Okay, that's a good question. I don't know if people will know run-ahead execution, so maybe I'll explain that a little bit. So it's my PhD thesis topic, and I really enjoy it still. I teach it to freshmen sometimes, actually, at ETH. So the idea is whenever you have a long latency memory access in the processor, out-of-order processors have limited instruction window sizes. And we wanted to design a mechanism that doesn't stall the processor whenever you have a long latency memory access. So existing out-of-order processors we analyzed at that time, they would stall quickly after the long latency memory access occurs, and they cannot do anything, they just stall for a long time. So the idea of run-ahead execution is not to stall, but do useful work using speculative execution. Basically, you checkpoint the architectural state whenever you get a long latency load miss that essentially fills up the window, and you get into the speculative execution mode called run-ahead mode. And during this time, the processor is speculatively executing instructions, and some of the data is not available, of course, because you missed on that. But the data that's available enables you to pre-execute these instructions that would lead to other cache misses, other long latency load operations. And now you can parallelize those long latency operations with the long latency operations that you would have otherwise stalled on. And this effectively serves as a nice prefetching mechanism. And whenever the original load miss comes back, you basically flush the pipeline, go back to the checkpoint and re-execute. And hopefully while you're re-executing, all of those instructions that would have otherwise been load misses have already been prefetched into the cache. I really like this idea. Of course, it's my baby, right? So how did we come up with it? We actually, I did 5 internships during my graduate school, during my PhD. The first internship, I worked with Eric Sprengel and the Pentium 4 architecture group at that time. And we looked a lot into prefetching, and we actually have a patent on how to reorder the prefetches and memory demand accesses in the memory controller, FSB, front-side bus controller at that time. And we were also looking at, okay, why you have these long latency memory accesses, how beneficial is out-of-order execution to tolerate it? How big should your buffers be to be able to tolerate these? And this got me thinking that maybe we should do something different as opposed to increasing the size of the buffers in the processor to make out-of-order execution even more effective. And next time I went for a second internship at Intel, Chris Wilkerson and Jared Stark, who were my mentors at that time, they were actually thinking in a similar way. And essentially, Chris was actually working on something very similar to what led to run-ahead execution. And we worked together, and we came up with the ideas that essentially is known as run-ahead execution today. So it basically started from the observation that maybe we should do something different as opposed to increasing the size of these large instruction windows. And it really came through as a collaboration between folks at Intel.
During your intern.
Exactly, during my internship. And if you look at the original run-ahead paper, I'm the first author. There's Jared, Chris, and Yale. So there are 4 authors.
That sounds great. So the next question. Oops.
You don't have to leave it there. You know. Yeah.
So run-ahead execution is a form of more aggressive speculation.
Yes.
When you studied this idea, did you consider the security concern with respect to side channel?
Okay.
It has become a really hot topic today.
Yeah, absolutely. That's a good question. You know, absolutely not. So, yeah, I mean, basically security was not a concern at that time. And until very recently, I would say, in the design of hardware. And I think this is normal because people were really designing microprocessors to be very high performance and low cost. And those were the 2 major design constraints for a really long time. Energy efficiency became a design constraint in the late 1990s and early 2000s. But right now, of course, it's a key design constraint, energy efficiency, power efficiency. Security was not even in the horizon, right? So that's why we didn't really think of any of the security issues that this could lead to, because it was really not part of the radar. I think this is normal, as I said. That's the evolution of computing. Over time, as you develop more sophisticated techniques, as you solve some of the big problems like performance, energy efficiency, reliability, at some point, maybe other issues become even more important. And I think right now security is very important. And clearly Run-Ahead is similar to out-of-order execution in the sense that it speculatively prefetches data into the caches that could lead to side channels, and it probably exacerbates the Spectre problem. But we need to change the mindset so that we solve those problems in a fundamentally good way. And I don't know how to do that, but I think it's good to do research on it.
So, like, before we move on to the next stage of your career, so we want you to compare the CS and ECE department of UT Austin, because we know at that time in the CS department there are also some architecture project like chips, and can you compare the differences?
I see. Okay, that's a tough question, you know. I mean, certainly comparing the two departments is hard because I don't know enough CS and ECE, but I could compare the style of the different projects. And I don't think this is really a function of the department. I think this is really a function of the advisor and their style of research at that point in time, because advisor styles also may change depending on what they want to achieve, right? So with my advisor, our style was, as I described it, was you focus on fundamental problems. Each student carves out their own thesis. You're relatively free in coming up with new ideas. So you can actually work on something that Yale was not thinking of at that time, and you go to Yale and describe your idea. If he thinks this is great, then you work on it and you do research on it. So it was a different style, certainly, and I like that style. The other style, at that time, the TRIPS project was going on, which is also a very important project, I think, at UT in the CS department. It was focused on building this large data flow-like engine that's distributed. I don't want to go into details, of course, but the key thing is really they wanted to implement this processor to demonstrate a prototype showing that this actually improves performance, energy efficiency, etc. And that's a very different style of research. Clearly, there's a very clear, defined goal, and there's a very clear idea. But now the important part of research is, for the research group, is to find out how to build this processor. And that requires certainly some research, but also a lot of implementation. And also requires a big group because you're really building a chip. So I think that's the fundamental difference between the styles. I think it really depends on what you want to do as a PhD student. If you have a choice between these two, it depends on what kind of a person you are. If you want to develop new ideas on your own, of course collaboratively with the group that you're in, maybe the first style is better for you. But if you really like building real chips, implementing, and you're okay with working in a large group together, and somehow figuring out what your thesis should be within that, working with your advisor, of course, then you'll need to, maybe that style of research is better for you. So I think it's really a trade-off in the end. There are pros and cons of both approaches. I think that finding a thesis topic is probably easier if you actually try to carve out your own path. Because in a big project, then if 20 people are working on it, the question is, will you be able to find 20 different thesis topics?
Right.
Of course, this depends on the project and the advisor and the student. So it's very hard to say that it's not possible, but it may be a bit harder.
So after your PhD, you first went to Microsoft as a researcher. However, your research topics have drastically changed from Run-Ahead execution and improving memory level parallelism to memory controllers and MLC. So what inspired you to choose these new topics?
Oh, that's a great question also. It's good to change your research topic once in a while, especially after your PhD, you know. So What inspired? So essentially, when I started, I was the first founding member of the computer architecture group at Microsoft Research, and a week after I started, Thomas Moshe Broda came to the office next door, and we clicked right away, and we started working together. And at that time, multi-core processors were just hitting the market, in the sense that they were becoming mainstream. Intel, for example, had Intel Pentium D, which you probably don't know because it doesn't exist anymore. But it was basically a replication of 2 cores. And we were very interested in, because his background is in distributed systems. Clearly my background is in computer architecture. And we were very interested in problems that are new to multi-core systems, because we thought those were the important problems to solve. I had some interest in memory controllers, of course, and while we were brainstorming, we said that definitely memory controllers will be a problem, because if you're putting all of these cores and they all have to go through the memory controllers, then you have a bottleneck here. And then we started looking into the algorithms that are employed in the memory controllers, and we found a lot of fairness issues. So the first paper we wrote was actually on memory performance attacks, and that was published in Unix Security. And similarly, NOC also becomes a problem, because if you're putting many cores on a chip, how should they communicate with each other and the memory controllers? So that was also a natural direction. So the real thinking was, can we do something big in the multi-core space, which is just starting, that will also remain fundamental? And I think memory controllers still remain fundamental. How to build energy-efficient interconnects remain fundamental. The first work we did in the interconnect part was bufferless routing, a case for bufferless routing for on-chip networks, which was published in ISCA 2009. I could go on, but that was the real the reason I wanted to switch. Actually, this later became we looked at memory quality of service quite a bit, but we also looked at some other fault tolerance issues at Microsoft at that time, and that was also important, I think. I always had this interest in fault tolerance, which later influenced my research quite a bit, as you can see with the Rowhammer problem, for example.
Yes, so I think that actually the next question is like already partly answered.
Okay,
so this question is that we noticed that you also published a paper in PODC, so on distributed system theory. So because you do architecture, how do you find that connection?
I see, yeah. I think I know what you mean by partly answered, but I'll explicitly answer it.
Yes.
So PODC is the top conference in distributed computing, principles of distributed computing. Right. I normally don't publish there, but Thomas, who was my colleague, he was in that community. And the problem we were working on, basically, how to design memory controllers that can provide quality of service to different requests, is certainly a distributed computing problem, because you have multiple memory controllers on chip. Then the question becomes, so if you want to actually provide quality of service, one of the mechanisms we developed was parallelism aware batch scheduling, which was published in ISCA in 2008. And one of the ideas in that work was to rank the threads in some order, such that threads that would benefit the most from being prioritized should go first, without, of course, destroying the performance of some other threads. I don't want to go into the details of the ideas. People who are interested can read the ISCA 2008 paper. Now, if you actually, this works nicely in a single memory controller, but what happens if you actually have multiple memory controllers? Now you really need to look at the requests in all of those memory controllers to be able to come up with a consistent ranking across those threads. So it's really a distributed memory controller problem. Now the question becomes, how do you actually design a mechanism that minimizes the messages between the memory controllers so that you're more efficient? And that's why this was a perfect example of distributed computing and computer architecture put together. Thomas did a lot of the theory part of the work. I did a lot of the practice and implementation part of the work, and we had a nice PODC paper. I think that's my only PODC paper.
Yeah.
But it's thanks to the collaboration that we had, actually.
That's an interesting topic. And after your time at Microsoft, you moved to CMU in 2009 as an assistant professor. So why did you make that choice?
Okay, that's a great question also. So essentially working at Microsoft was great. I had a lot of freedom because I was the founding member of the computer architecture group, and we hired a lot of great people also. But I was also actually working with a lot of interns also. But I wanted to teach, and I also wanted to maybe work with students even more closely for a longer term, like 5 to 6 years. And it's very hard to accomplish something like that in an industrial research lab. Certainly not a product group, but not also not a research lab. And that was the major reason. And I really enjoy teaching. You can do some teaching when you're in industry, but you don't get rewarded much for it in the end. So as a result, that cannot be a big chunk of your focus. And I enjoy the teaching and mentoring part of being a professor quite a bit, in addition to the research part.
That's very nice.
Okay.
Yeah. So the next question is, what is the difference between your academic life at Microsoft Research and the CMU?
Okay, what's the difference? That's a good question also. I think I gave you some differences. Basically,
yes.
at MSR, or in industry in general, even though MSR was also somewhat academic at that time, it's one of the finest academic research labs in the world. It changed a bit over time, but still it has its academic flavor. Essentially, I think one of the big differences is how closely you work with students, whether or not you teach, and whether or not you will be constrained at some point. I think these are the 3 key differences I should probably mention. Clearly in industry you don't work as closely with students, even though you may have a lot of interns, they come and go, so you don't mentor students for 5-6 years, which is the length of a PhD. You certainly don't see a lot of undergraduate students or master's students or high school students. That doesn't happen unless they come for internships, which is not the common case. So working with students that's what you do in academia for sure. Teaching, again, as I mentioned, you don't get rewarded much for teaching in industry. You could certainly teach in some local school around you, but that's extra effort for sure. Whereas teaching is a fundamental part of what you do in academia. And if you want to become a professor, it's a good idea to teach, to like teaching. And the third one is, I think, about the long term. So while I was at Microsoft Research, it was great because I had a lot of freedom. But the question always is, how long will your research freedom last in an industrial setting? And I think this is a fine, important thing to think about. If the academic research lab lasts for a long time and it becomes as free, that's great. But it turns out that's not the case in most existing examples. And even if it's true, usually at a company, you want to contribute to something in company, and which is not a bad thing actually. If you go to an industrial research lab, I think you should definitely contribute to something in company. But this may also restrict your freedom in terms of what you want to do at some point, because you will really be working on some product line research, even if it's research, and sometimes you will be working on products actually. I think that those 3 are the fundamental differences. There are some other differences, but I don't think they're as fundamental.
I see. So at CMU, you change your research direction slightly again, from memory access, scheduling, and NOC to memory problem from all angles. So why are you so excited about this memory problem?
Okay, that's a good. Well, I think it's obvious, right? It's the biggest bottleneck that we have in computing systems today, in my opinion. Essentially, if you look at processors, most of their time is spent waiting for data coming from memory, and most of the energy in a system is spent waiting for data coming from memory. And we recently wrote a paper in ASCLOS in 2018 where we analyzed 4 key workloads in mobile systems that are used in Android and Chromebooks, essentially Google's workloads. And we found out that more than 60% of the energy is in data moment. And we knew a lot of this before, actually. When I joined CMU, I was very interested in all of this. But I should also correct that I didn't really abandon the memory controller research, and we continue doing memory controller research, actually. We're still doing some of that.
Yeah.
But I also added some more research topics. For example, we had started working on non-volatile memory, phase change memory while I was at Microsoft Research, but we continued working on that and hybrid memory systems. The DRAM scaling problem, how to attack the DRAM scaling problem, that really started at CMU actually. That's because we wanted to really tackle the DRAM scaling issues. Non-volatile memory was certainly very interesting, but it was very speculative. But DRAM, clearly, everybody uses DRAM, it's everywhere. And we wanted to improve that, and that started at CMU for sure. And I can go into more detail, but I don't know how much time we have. Okay.
And then in CMU, your group discovered this Rohammer problem in 2014.
Mm-hmm.
And how did you find this problem is now very important, both in industry and in research. And
Mm-hmm.
how do you find this important problem?
Yeah, that's a great question actually. Now you asked the right question. Now I can talk more detail about the DRAM scaling.
Yes.
So we were looking at how to scale DRAM into the future, meaning how can we reduce the size of a DRAM cell while keeping it reliable? So we were looking at issues like refresh, because one of the issues, the critical issues in scaling DRAM is how do you determine the retention time of a DRAM cell? It becomes more leaky. It becomes more vulnerable to these quantum-like effects, random effects that change the retention time. So we actually started the problem by looking at refresh. How can we get rid of refreshes? We also looked at another angle, which is how can we improve the parallelism, overcome the long latencies, but that's not as related to the Rohammer problem, so I'm going to focus on the refresh. So while we were working on the refresh problem, we built a lot of infrastructure. These are FPGA-based testing infrastructures, so that we can test DRAM chips, figure out the retention times, figure out the latencies, and figure out when they failed, at what retention times. Concurrently, we were also working on a flash memory infrastructure. We actually, our first publication on using FPGA-based testing infrastructures on flash memory in date in 2012. We were looking at error mechanisms, reliability mechanisms, similar scaling issues in flash memory. And we saw a lot of read-disturb effects. And we already started thinking that some of these read-disturb effects may be present in DRAM as well. Basically, read-disturb means that whenever you read a row in memory, you disturb the adjacent rows. That's true for flash memory also, actually. That's true for hard disks. That's true for phase change memory. That's true for SRAM. And we asked the question, maybe it's also true for DRAM. And we had this infrastructure built. And we also, one of my students, Yoongu Kim, he went to Intel as an intern in 2012, summer 2012, actually. I spent the summer 2012 at Intel also for a couple of months. And he started also looking at those issues at Intel at that time. And when he came back, we used the infrastructure and our collective thinking to test if this problem also exists in DRAM chips. And we found out that actually they were vulnerable. The real DRAM chips were vulnerable to these read-disturb effects. Now it's known as the Rohammer problem. So I think and we wrote a paper together with Intel folks, which was published in ISCA 2014 on this topic. So I think what enabled us to do this is really three things. One is we were already working on memory, different types of memory, flash memory, and we had clues in flash memory that read-disturb is a big problem. That enabled us to think, it may be a big problem in DRAM chips, existing DRAM chips as well. The second thing was we built this infrastructure to test DRAM chips relatively easily using FPGAs for some other reason, which was to check the retention times. We already had it available so that we can test Rohammer. And the third reason was the collaboration with Intel that enabled us to gain more insights into the problem and then solve the problem also.
So again, on your papers, among all your papers, in your opinion, which one is the most important?
I don't know if I can answer that question, because I like a lot of my papers. Everybody should, I think. But they're all your babies, right?
Right.
How are you going to choose between your different children?
Relatively.
Maybe top three.
Top three, yeah. How about top
10.
20?
Maybe pick some from the top 20.
Okay. So let me think. I like a lot of them. So run-ahead paper, of course, is a baby, right? This is an HPCA 2003. That's my first paper. That's my thesis paper. I look back, it's not written as nicely. I can write it better, so I rewrote it for my thesis. So I think, I like it. I don't know, I don't want to rank them, but Let me do it chronologically, maybe. Some things that come to my mind.
Sure.
At Microsoft, we wrote this memory performance attacks paper that I mentioned. I really enjoy it. I think it opened up a lot of research in memory controllers in using security. One of the papers that I was the first author on at Microsoft Research was parallelism over batch scheduling. This is one potential solution to the memory quality of service problem, and variants of this is implemented in Samsung, some of the Samsung SoC memory controllers right now. I like this paper a lot because I think it's a good example of how to write a good paper. I actually recommend that to my students to read and to follow as an example. Let me think. We wrote this bufferless routing paper at Microsoft. I like that also. We wrote the first PCM paper, one of the first phase change memory papers, together with colleagues at Microsoft, which was published in ISCA 2009. Of course, the Rowhammer papers, exciting. I cannot say. That's also one of the babies. Another paper is Radar, a retention aware intelligent DRAM refresh, which we published in ISCA 2012. That opened up a lot of research, a lot of work, including ours, but other people in the field, in terms of how to reduce the refresh problem, how to get rid of the refresh problem. Another one is subarray level parallelism. That's, I think, very important also, because that gets rid of a lot of the bank conflict impact. And that was also picked up by Samsung and Intel. They wrote a paper in memory form in 2014 saying that this is a good idea. It should be used in future products because it enables us to tolerate long latencies that we have because of bank conflicts. Let me see. I'm sure I'm missing a lot because there are a lot of papers, but I'm going chronologically, so I already missed a bunch. Don't worry. I mean, I like the works that we've done on processing in memory for sure, like Vivek's work on row clone, essentially cloning pages in DRAM without going through the processor. That's very fast. And then his later work on mbit, which is doing bulk bitwise operations in DRAM. I think these are very forward-looking works. We did other work on 3D stacked in memory computing, like Tesseract, work in ISCA 2015. It's hard to pick, you know.
They're all wonderful papers. They are all wonderful papers.
I think so, yeah. I'm glad you think so as well. I mean, we can keep going also. I mean, more recently, we recently published this paper. This is, again, based on the infrastructure that we've built over the years. This is a paper in HPCA 2019, and it shows that you can actually generate random numbers in DRAM, true random numbers in DRAM, by reducing the latencies. And once you reduce the latencies, you get some cells failing at 50% rate. They're essentially random number generator cells. If you have a mechanism that profiles these cells, you can essentially generate true random numbers without changing DRAM at all, by just changing the memory controller at high throughput and low latency. And this was enabled because of all our research that we've done in the past, understanding of the DRAM that we built.
Sounds great.
Okay. I can go on and on, I think. But I think we have limited time, so
Yeah.
I'll refer people to the papers that are on my website.
Yeah. So, like, speaking of time, so our next question is, so you have many papers, like especially in ISCA, you have more papers than anyone else in ISCA, and the question is, like, how do you manage your time? How do you manage your students to produce so many papers?
Okay, that's a good question also. So, okay, let me first say that the goal is not really to just write papers. Papers are a means to an end.
Yeah.
I think my goal has always been, how do I solve a problem such that it can make a big difference in the world, have high impact essentially. And I think to be able to have high impact after you need to generate a lot of good ideas. First of all, you need to pick a big, important problem. You need to generate good ideas to solve that problem. And you need to do all the right things such that you get good results showing that your ideas are actually good at solving the problem. And then the next step is really writing the paper to show to the world that, okay, this is a good idea, or this is a mechanism that you should consider. So I think that's the steps that I follow. And I think this naturally leads to certainly papers. How I guess your question was,
Yes,
how do you write a lot of papers?
Actually, it's like how do you manage your time and
okay.
how to manage the students.
I see. Okay. So I have a big group that enables a lot of papers, so we can focus on a lot of topics. I work with them closely, but I also give them a lot of freedom. So I suggest, essentially, I enable a lot of creativity in the students, and I try to pick students who can actually work independently. Not all the time, of course, but who have the potential to work independently. So I think that enables a lot of new ideas coming out collaboratively with my students, and also encourage my students to collaborate with each other so that they can actually help each other. They can push back on each other so that they can develop a lot of ideas. In terms of managing, that's how I manage my students. And I give them a lot of freedom. So if my students are doing well, for example, then I enable their freedom so that they can develop big ideas. I just give them the right feedback so that they can find their path in a nice way. How do I manage my own time? I mean, I work hard, so I think it takes a lot of effort to do a lot of good work. So there's no, I don't think there's any shortcut. But I also try to. I mean, of course, sometimes it's stressful, so you need to find mechanisms to minimize your stress. So I swim a lot. That's the thing that I do. I swam this morning at 6 a.m. Until 7:30, I think. So it took 90 minutes today. Okay. No, I think it was longer. It took 100 minutes until 7:40. Yeah. But it was very nice because we're in Phoenix. You can swim outside and it's beautiful. Yeah. So I think you work hard, but you also play hard. You figure out the best ways where basically do what you like. I enjoy what I'm doing, so I don't feel like it's really work. I think research is really a lifestyle for me. Living that lifestyle. But I'm also adding other stuff that I think should be part of my lifestyle that I enjoy, like swimming and traveling. Does that answer your question?
Yes. So one side question, like how long distance can you swim in?
How long
do you swim slow? Because if I swim for 60 minutes, I would be. I can't even imagine this.
So okay, that's a good question. I mean, I don't know what the distance is. I guess you could calculate it probably. But I don't swim extremely fast, of course, right? I don't swim very slow also, because I think I swim definitely faster than average swimmer that you find in a reasonable swimming pool, not in a kids playing swimming pool. What was the question?
What's the distance?
What's the distance? I see. Yeah, I don't know the distance, I guess. But I had some other comment that I forgot right now. I was going to make. But it's I mean, you can do the calculation, right? It's 100 minutes. It's definitely more than 4 kilometers or so, I think.
Wow.
Yeah, in 100. I believe so, but I have to check that, you know.
So back to the students.
Okay.
So you mentioned that one criteria when you choose students is their independence. So do you have any other criteria, and will you encourage them to go to academia?
Okay, that's a good question. Before I get to that, now I remember what I was going to say. So I've been swimming, not recently, I've been swimming for more than 10 years. That's why it's become faster over time, and I enjoy it. It's really an activity that sometimes replaces sleeping for me. When I swim, I come up with new ideas. I also sleep a little bit. So it's good. Okay, so your question was, do I have any other criteria for selecting students? What was the other one?
And will you encourage them to go to academia?
Okay, these are two separate questions. Let me tackle the first one. Well, the first one is, I think it's an art. It's not easy. Certainly independence is a good metric, but I want it all in a student. So creativity, hard work, resilience. I think really wanting to do a PhD, and basically I think the key thing is perhaps resilience in the end, meaning you set your mind to do a PhD and you're going to do it no matter what, and of course you need to have the right ingredients in the sense of creativity, hard work, and also working well with people. I think that also helps. So I try to look for these different things. But I mean, there's no single algorithm, I think, to select good students. And PhD is a long road. It's not. It starts. It can go up to 7-8 years. Hopefully not. I took 6 years in my PhD. It was good. I'm glad I graduated within 6 years. I probably wouldn't want it to last longer. So I think resilience is really important. But of course, I think you need to have the other characteristics as well. Basically, I think you need to really have the right mindset while you're getting into a PhD. And I think that this is really... I look for a click between the student and me. If it really clicks between the student and me in terms of the style of work, style of thinking, that really helps, for sure. Do I encourage them to go to academia? I don't strongly encourage them to go to academia. It's of course good for students to go to academia and become professors, but I think this is really up to the student in the end, because academia is certainly different from industry. And if you really don't like teaching, for example, maybe academia is not that great for you. But if I think a student should go to academia because I think he would be a great teacher, great researcher, great professor, I definitely encourage students to go to academia in that case. And I think I've encouraged a lot of my students to go to academia, but most of them end up going to industry, which is not bad, of course. If that's what they want to do, that's great. But I think one thing to consider after you're done with your PhD is if you go to industry, it may be hard to get back to academia. If that's really what's in your heart, to go to academia, and you're making a decision after your PhD, you might want to think twice before going to industry. Because once you go into industry, especially if you get disconnected from the research community, if you stop publishing, if you stop being visible in the community, it's very hard to go back to academia. You'll need to do a lot of work to go back to academia. Whereas the other way is not hard. It's not as hard. If you go to academia, you become a professor, you enjoy it, and you decide, okay, it's time for me to switch to industry. It's usually not that hard, because there are a lot of, and the reason is very fundamental, right? There are many industry jobs compared to academic jobs. It's usually harder to get an academic job for that reason. Right. Positions are scarce.
Yeah, and the next question is, you recently moved to ETH. What's the difference between ETH and CMU, Europe and US?
Oh, okay, well, those are different questions, you know. Europe and US is different from ETH and CMU. Oh. Let me start with the ETH and CMU first. I think they're both top schools, and that's the reason I moved to ETH, because it's really a top school. It's really, actually, I think in many of the rankings, it's maybe top in the world in computer science. Of course, I don't believe in all of the rankings, but rankings say something also sometimes. So there's a lot of good research support in ETH. So what are the fundamental differences? Well, one is in Switzerland, one is in the US. I think Switzerland is nice. US is also nice, but I think one of the big differences is CMU is a private school. ETH is a mostly federally funded school. From a professor's perspective, I get a lot of funding from the Swiss federal government, and that's very generous. So I don't need to write as many grants as I needed to write at CMU. At CMU, basically, as a professor, you need to write a grant for every student that you want to support, which wasn't a big problem for me, but you spend a lot of time writing grants, so you don't have a lot of time for other things, maybe, like working with your students or generating new ideas. So from the professor's perspective, I think there's this fundamental difference. I'm not sure from a PhD student's perspective. I think they're both top schools. In the end, you'll be working with your advisor is probably more important than the school you're in. As long as the school provides the right environment so that you can have enough resources, and also the intellectual environment where you can interact with many other people and collaboratively work with many other people. And both of these schools actually do, because they're top schools. From a PhD student's perspective, I don't think there will be much of a difference. It's really about who you're working with, in my opinion. Let me think if there's anything else. Yeah, I think those are the fundamental ones. In terms of US and Europe, that's a much different question, because Switzerland is not necessarily Europe. I mean, it's in the middle of Europe, yes, but it's not part of the European Union.
Yes.
And the universities in Switzerland are, I will say, are slightly different from the universities in other parts of Europe. The European style sometimes is different. So Swiss universities, I would say, are closer to the US universities, or maybe it's a mix of US and European style universities, but it's more closer to the US universities. Especially the approach I take in working with my students is very much similar to the approach I take I took at CMU. So from that perspective, I don't think there's much difference.
Okay.
So in recent years, you did intensive research on bioinformatics, which is not a traditional topic in computer architecture. So can you tell us more about how you found this topic and what excited you the most?
Okay, that's a great question. I like that question. I actually give talks describing how I started in this one. So it's again, this one started collaboratively with one of my friends. He was at the University of Washington Genome Sciences Department. He was doing a postdoc over there, Can Alkan. He's now a professor at Bilkent University in Ankara. And I was at Microsoft Research. And essentially, he was doing a genome analysis. He was very interested in building mappers, for example, read mappers to do fast genome analysis. And we started talking about this, and we went on a hike together at Mount Rainier in 2007. And we did a lot of brainstorming during that hike. And one of the things that we were both very interested in was actually designing very fast genome analysis mechanism, because at that time, if you look at genome analysis, the tools that were there to reconstruct reads and map them to a reference genome, this is called sequence alignment or read mapping, were extremely slow. And this is the first fundamental part of the genome analysis. If you want to ask questions like, where do these different genomes differ, what is your vulnerability to a particular drug or something, you need to first reconstruct your genome. And that takes a lot of time. If it takes 2 weeks, then you have no hope for quickly generating an answer, which you may need in real time, right? At that time, we actually envisioned embedded devices that could do these analyses really fast. Of course, you needed to do research in architecture as well as bioinformatics to be able to enable that. So we started doing research in software to begin with. How do you design these mappers that are very comprehensive, that can do genome analysis? How do you make them really fast? So we had a lot of software papers. The first one was in Nature Genetics in 2009. And then later we had a paper in BMC Genomics on software methods for accelerating it really fast. And then we had a bunch of papers in bioinformatics to accelerate these mappers using FPGAs, and we looked at GPUs. We also looked at in-memory processing techniques more recently. So that's how it got started, and now it's a relatively large effort in my group. Actually, I graduated my first student who worked on genome analysis last year, Mohammed Alsar. He was co-advised with Can Alkan. Now I have 5 students working on bioinformatics, but it's not just bioinformatics. It's really system design for bioinformatics. How do we design systems for bioinformatics? Of course, with a lot of knowledge about the bioinformatics at the higher end, so that we can make things much faster, much more efficient, such that we can enable large-scale processing of a lot of data. Because we can actually generate a lot of genomic data today, because people were able to build genome sequencers that are very high bandwidth.
Sounds cool.
Yeah.
So what do you personally feel excited most about it?
About the genome analysis?
Yeah.
I think it's a really critical problem for enabling new applications that we may not even think of today. That's the way I see it, basically. We don't know what we can do with genomes if we can analyze them extremely fast. Certainly I can think of medical treatments, for example, right? If a doctor is treating a patient and it's life critical and they need to make a decision as to which drug to administer, they can make that decision very quickly, right? So I think that's what I feel really excited about. We can enable this sort of medical treatments that are really important for people if we actually succeed in this research. So the impact, in my opinion, the impact will be huge. That's what I'm really excited about. And also, it's not just medical treatments, it's also scientific discovery, right? If we can analyze many genomes very quickly, maybe we can enable a lot of new discovery as to the origin of species and different relationships between different species. So basically, I don't know what we can enable, but it feels like we can enable a lot. That's what makes me really excited.
Okay. So this question is about China. And over the years, you have several Chinese students and visiting scholars, and you have also visited China several times. So what do you think about current architecture research in China?
Okay, that's a good question. I like China. I've been to China actually not several times, 8 times, I think right now. And I'm going there in August again to give the keynote speech at APPT conference in Tianjin. I don't remember exactly when in August, but late August, hopefully. And I have had a lot of Chinese students. Yixin was the last one to graduate, I think. Yes. And I work a lot with Yukai, for example. He did a lot of seminal work on flash memory. Yixin's thesis was on flash memory. He did a lot of seminal work on flash memory also. And I still have some Chinese students in my group. So you're asking about the Chinese students, or you're asking about
the Chinese architecture research?
Okay, I see. So that's a good question. I think certainly a lot of there was not a lot of architecture research in China, as far as I know, when I was a graduate student, when I started as a graduate student in 2000.
Yeah.
Certainly there were a lot of Chinese who were in the architecture community, right? I mean, Wen Mei is Chinese, right? That we mentioned. But over time, I think in the last, let's say, 20 years, China definitely improved, maybe exponentially. I don't know, of course, I'm just making up this curve. Probably they improved exponentially in terms of how they generate ideas. Certainly we see a lot more papers from China right now in architecture conferences. And I also feel that maybe during the early parts of the architecture research in China, it was much more implementation focused as opposed to idea focused. I think it's maybe that barrier is overcome right now. There were a lot of good people who started being idea focused, and I feel right now there's a lot of creative research that's coming from China in architectures, and I expect there will be a lot more going into the future. Yes, I don't know if that answers your question fully.
Okay. So this is the last question. In architecture, there are 3 main conferences: ISCA, Micro, and HBCA. For our students, they look similar. If one paper gets rejected by one conference will just resubmit it to another one. So that is a very interesting phenomenon. But it seems that they're managed by 3 organizations: SIGARCH, TCC, and SIGMicro. Is this due to some historical reasons? And is there something that can be done to further improve our community?
Mm-hmm. Okay, that's a lot of questions. That's a tough question, actually. So you mentioned 3 conferences: ISCA, Micro, HBCA.
Yes.
I would add a 4th one, ASPLOS. But it's a bit different because it's really multiple communities: architecture, programming languages, and operating systems. So I'm going to ignore that one for now, even though I think a lot of architecture people publish also in ASPLOS. But I think I understand your question, because usually you may not submit to ASPLOS if you get rejected from one of those because you may want to look at a fit. So certainly these 3 conferences started differently because of historical reasons, and different people started the different conferences, and as a result we have these different organizations managing the different conferences. And I think that's a good thing because it enables diversity in the community. It's always good to have different voices handling different things, and I like that diversity. And this is diversity in terms of people. It's also diversity in terms of thought. I can give you a little bit of history in terms of why these started differently. Actually, Micro was the first conference among all these 3, It started in 1968, I believe that's true, but you could check also. And it started as a workshop, actually. It was a workshop on microprogramming. At that time, people were very interested in how to do microprogramming better. And incidentally, microprogramming is invented by Maurice Wilkes in the 1951 paper that I mentioned during my award speech today. I'm very honored to receive an award that's named after him. But Micro started as a microprogramming workshop, and it was both hardware and software, because if you want to, for example, reduce the size of your microcode, you actually need to design a good software mechanism to reduce, to do the same thing with smaller lines of code. It's essentially compilation, some sort of compilation, or some sort of software optimization. So Micro's roots, as a result, have compilers as a very fundamental part of the conference. It's also hardware, of course, because microprogramming is at that time, all of the machines were microprogram machines. And over time, clearly, Micro evolved quite a bit. It became a full conference, I believe, in 1992. So it was a workshop for about 24 years. It became a conference in the 25th year. And at that time, it was about microarchitecture plus compilers, really. So it broadened up. It was less about microprogramming. You see fewer and fewer papers on microprogramming over time. You see 0 papers on microprogramming right now, because it's not about microprogramming anymore. And right now it's much more broad. Of course, it's similar to ISCA in scope, but it's also slightly different because ISCA or HPCA don't have this compiler aspect. And also Micro doesn't have some aspects that ISCA and HPCA have. ISCA and HPCA, for example, have more higher level system components aspects like networking sometimes, storage sometimes, although that's also going into Micro and HPCA, Micro recently. So I think because of the things, because of the way research topics and interest of the communities have evolved, conferences start resembling each other more and more, but they're also slightly different. Now this is, I think, again good, because now we have 3 conferences where students who are interested may submit papers to, that enables more opportunity to get your work published. And also these are 3 diverse conferences, so for some reason Conference A may not like your paper, but Conference B may be very receptive to it. And I think it's good to keep that healthy diversity in the community for sure.
So in terms of the community, is there any advice you can think of that can improve it?
Oh, okay, that's a hard question. That's not I mentioned that a little bit in my Maurice Wilkes talk today. I think our community has improved a lot. It's become much more diverse and nicer over time, for sure. I think we can improve the review system. I see one of the biggest problems that our community faces, biggest challenges that our community faces as the review system today. How do we handle the reviews? And is it really fully merit-based, or are there other factors that are affecting the reviews? I think a lot of people have complained, rightfully so in my opinion, that papers get rejected sometimes for arbitrary reasons. And I've experienced that also, as I've shown examples of. For example, the Ambit paper got rejected 4 times. It was this is the paper that enabled in-memory block bitwise operations, and several of the times the rejection reasons were, okay, this is a great paper, novel idea, clever idea, but DRAM manufacturers will never implement it. I will consider this as an arbitrary reason to reject the paper, because well, how do you know, right? This is not a very scientific reason, right? How can you prove that DRAM manufacturers will never implement it? It's not a flaw in the paper, basically, that you're pointing out. So I think we need to fix such issues, because if these papers get rejected arbitrarily, there are multiple bad consequences to it. One is, I think, scientific research gets delayed. And we've experienced this with Ambit, actually. We published it 2 years after we developed the ideas. But we put out a technical report online called BuddyRAM at that time, and other people built on Ambit using that technical report. So they published papers earlier than us that built on Ambit before we could publish Ambit. So we enabled scientific research, which is good, but I think this out of order thing is not good. But they did cite the Pinatubo work in DAC in 2016. For example, Yuan Shei's group developed it. They did cite Buddy Rap as one of their inspirations. But I think this is not sustainable if we keep arbitrary rejection. So I think we need to solve this problem of reviewer accountability in the system. So how do we solve it? I mean, this is, I think, beyond the scope of this conversation. I think we need to think about potential solutions, brainstorm about the solutions. But I think the first step is really making this a first-class citizen in one of the problems to solve. And it's important for the students also, because it hurts to get your papers rejected arbitrarily, right? Of course, you should be resilient and keep working on it. You should believe in the work that you're doing, be passionate about it, but it still hurts as a student. Yeah, it does.
So that's all of the questions we have. Congratulations again on your award. I'm sure our readers will enjoy our interview.
Okay. Yeah. Thank you very much for the interview. Thanks for your time also.
Thank you.
Thank you. Okay, did it work?
Yeah. We could also take some pictures. So
okay,
that
sure.
we'll use. Maybe later I will ask some pictures from you, so that it
Okay.
can be included.
Okay, sure. Yeah, we could take pictures if you want.
Pictures here. Oh, I should first.
No, stop.